Hi, I'm Peter Rowlett.
And I'm Katie Steckles. And Peter, what is today's mathematical object?
Well, today I have a game. When we started a podcast about mathematical objects, obviously one of the first things I thought of was the game Quarto. And here we are, 6 seasons in, finally getting around to doing Quarto.
Yep. For
some reason. Quarto is a game, if you don't know it, it's this... You can buy a version of it. It's this quite nice sort of board with wooden pieces on. And it's a sort of noughts and crosses-ish game. It's a 4x4 grid, and the aim is to put things in lines. The pieces that you've got, what's sort of interesting about the game is that the pieces have 4 attributes. So each piece is either tall or short, and it's either black or white, and it's either round or square, and it's either got a flat top or it's got a dimple in the top. I feel like that's the awkward one. All the others are sort of quite clear. But the dimpledness is the slightly strange one.
Dimpleosity, yeah.
And the aim of the game is to put 4 pieces which all share one of those attributes in a line.
Okay.
That's how you play Quarto. So it's not like noughts and crosses where you're trying to get 4 crosses and I'm trying to get 4 noughts in a line, or 3 or whatever. Here it's 4 pieces that share some attribute, and we can both win at any point. So it's an impartial game. We can both. We don't have our own pieces.
Yeah, so it's not like, even though half the pieces are black and half the pieces are white, it's not in any way like chess in which one person only moves the black pieces and one person only moves the white pieces. So
yes, definitely.
On your go, you can pick one of the pieces. Oh no, you don't pick one of the pieces, do you?
So we'll get to that, yeah. So,
but you could be playing any of them, I guess, is the point. Yeah. I
have seen people who didn't bother to read the rules separate the pieces so that you have the white pieces and I have the black pieces, and that is not how the game works. Everybody plays any of the pieces. The other twist then is that you don't choose which piece to play. What you do is you choose a piece, you hand it to the opponent, and they play it.
Okay, so that I guess a turn consists of choosing a piece, giving it to your opponent, and then playing it, and then they choose a piece and give it to you, sort of thing. Yeah.
It depends how you think of it, right? I think a turn is playing the piece you've been handed and then handing a piece to your opponent.
Yeah, okay. So the game begins with half a turn and then proceeds. Okay.
Yes. So the aim of the game then is to get your opponent to hand you a piece so that you can put that piece down to be the 4th in a line matching some attribute. And this sounds ridiculous. It's helped by the fact that each combination of the 4 attributes is used once. So there are a limited store of pieces. Because there are 4 attributes and those attributes are binary, they can take 2 values. That means we've got 2 to the 4 different pieces, which is 16. Okay, so there are 2 heights, there are 2 colours, there are 2 shapes, and there are 2 dimplednesses, whatever that is. So there are 2 times 2 times 2 times 2, which is 16 available pieces. So eventually you start to run out of pieces, and the person just has to, I have to give you a piece that is neither tall nor short, and I can't do that. So
like there's a place you could play a tall piece that would win and a place that you could play a short piece that would win.
Yes.
So I'm kind of stuck.
Definitely.
Yeah, I mean, I guess the thing that immediately comes to my mind is, therefore, if there are 16 spaces on the board and 16 pieces, is it possible to fill the whole thing without having made a line of 4?
Yes. So games can,
so you can have a
end
draw.
in a draw. Yes, that's right.
Right.
Yeah. There are loads of nice puzzles like that. Is it possible to get, precisely one of each attribute in each row and column? There are all sorts of games you can play with these sorts of pieces. So how you play it is that you sort of keep handing pieces about, and then eventually somebody wins. And often at that point you sort of unwind. I don't know if this is common that people do this, but often I do this. You get to a point of winning and you think, what if I hadn't given you that piece a couple of moves ago? What would have happened differently? And often you find that the win actually occurred several moves before you realised it had, unless you're particularly good at thinking ahead in these things, that you've sort of started yourself down a path. And I mean, I think fundamentally this game is noughts and crosses. It's just that it is more complicated, but in a way that kind of adds to your cognitive load, but doesn't necessarily make it any less of a just search the game tree and look for a winning combination. And my sense is that it's probably a draw overall. But it's quite hard to play. And what tends to happen is that people who haven't played it a lot, it's really hard to keep track of all 4 pieces. Sometimes people forget that the other player can play the piece that they can play, so people get very possessive about those 3 dimples in a row are mine. How dare you put the 4th dimple in a row? And therefore they hand the other person a dimple, forgetting completely that they can actually play that. And the other thing is that it's very common that somebody loses one of the attributes. So they can keep track of 3 attributes and they can't keep track of the 4th one until they've practiced.
So I've done that. I've done that enough times.
Yes.
Like, I forgot about shape.
Yeah, definitely.
It's sort of it's the fact that you're trying to keep track of all those different things at once, but it's also frustrating to know that in theory, in any given situation, you could fully analyse the whole thing and go, okay, well, if I gave them this piece, they could do this. But it's, as you say, it's sort of rolling that forward a few moves ahead and having that sort of strategy to decide, if I do this now, then next time there won't be any pieces that I can give them or whatever.
So quite often you end up having to block a winning line because you know that you can't get the winning piece for that winning line, and in a couple of moves you're going to be forced to give it to the other person. So you block the 3 that are all tall because you know that you can only hand over a tall piece in a couple of moves time or something like that.
Yeah.
Anyway, where it gets interesting, because I'm a mathematician,
right?
So we I don't know, around when I was first playing Quarto, there was a student who was doing their final year project on noughts and crosses in game theory. And they were interested in this as to whether it was a noughts and crosses game. But it's very complicated as a 4x4 game. And so we said, well, all right, so you've been analysing the 3x3 noughts and crosses. Let's just make a 3x3 version of this. And then you can think about that, and then that'll be more like the thing that you're thinking about. So we have this games club called the Maths Arcade, this sort of optional thing. Students sort of drop in and play games, and staff come along and things like this. So I'm playing Quarto with this chap, and basically we took a 3x3 subsection of the board, and then tried to work out which pieces we need to throw away in order to have the 9 pieces for this board. And basically it doesn't work like that, because as I said before, you've got 4 attributes, each of which can take 2 values. So you've got 2 to the power 4, which is 16 pieces. If you do a 3 attribute version, you've now got 2 to the 3, which is 8.
Yeah.
But your 3x3 board has 9 spaces on it. Yeah. Which is fine. You could just play that, right? But it's not quite as satisfying because you can't fill the entire board at any point.
I'm sort of thinking, can you do a 2x4 board? But then that doesn't make sense because some of the winning lines would only have 2 things in, and some of them would have 4.
Yeah, I think with any games like this, you can play around and make something up that would work. But that would be a little bit. It's because it's easy to match 2 that share in 1 attribute, I guess.
That's a lot more.
That's a bit of a problem. So anyway, I reckon under the condition that you want the same number of pieces as you have spaces on the board and you want a square board, you can't do a 3x3 board.
Okay.
You haven't got the right number of pieces. So this then got us thinking about which ones can you do, right? So I'm going to say some letters, and you have to try and keep track, I guess. But if you have m attributes, then you have 2 to the m pieces.
Yeah.
And if your side length of your board is n, then you have an n by n board. So for those 2 things to be the same, for you to have the same number of pieces as you do spaces on the board, you need numbers m and n such that 2 to the m is equal to n squared.
Yeah.
Now, when I've got a 2 to the m on one side, I want to take log to the base 2 of both sides to get rid of that. So if you take log to the base 2 of both sides, you've got that m is equal to 2 times log to the base 2 of n.
Yep.
So what that tells me is that for this to have an integer solution, which I think I want,
ideally,
a game I'm going to actually play, because I've got a log to the base 2n term in there, I need n to be a multiple of 2, which is why 3 didn't work.
Yep. And
it started with a 2. It was 2 log to the base 2 of n. So that tells me that m needs to be even.
Yep.
So that's fine. I can make different viable games. So for example, if I've got 6 attributes and an 8x8 board, that would give me 64 pieces on a 64 square board.
Yeah.
8 by 8 is 64, 2 to the 6 is 64.
Some kind of terrifying mega chess. Yeah.
Yeah.
Okay.
Well, my other one here, so I do a bit of this in class with students. So I have a couple of casual examples. Why not? If you've got 14 attributes, then you need a 128 by 128 board, and you would have 16,384 pieces. Why not?
Yeah. I'm just trying to imagine what 14 different attributes you could have.
Oh, I know, that's the problem.
Well, you very quickly run out of things that you can vary, because you can only have... I guess you could have it stripy in 2 different colours and vary the 2 different colours, or...
You could have different patterns. You could have... You very much run out when you're trying to make your 2 to the 14 different pieces.
Yeah.
A way of thinking about that then is to introduce a notation. So my notation, I just made up a notation. I label things, but they're binary attributes, so I'm going to use a binary number system. And I just decided to make the order be color, size, shape, and dimpledness. And I've made white be 0 and black be 1, and then short be 0 and tall be 1, round be 0 and square be 1, and dimpled be 0 and flat be 1.
Okay. I'm very pleased that you've gone for that assignment, because 0 is shorter than 1, 0 is also rounder than 1, and 0 has a hole in the middle. So that all works.
Yeah, that's true. I don't know if 0 is whiter than 1.
I don't know.
Yes.
I mean, the middle bit of it is, but only if the paper is white.
Yeah. So if I'm doing binary strings or binary numbers in that order, like if I've got 0, 1, 0, 0, that's white, tall, round, dimpled. If I'm doing 1, 0, 0, 1, that's black, short, round, and flat topped. That's then a system that I can use to notate these pieces. And now I don't care how many attributes there are, and I don't need to think about whether they're stripy and also got a spiky top or whatever. I don't have to think about it.
Yeah.
It also gives me that the winning condition is met if 4 pieces in a line have 1 digit in common. So I just gave the examples of 0, 1, 0, 0 and 1, 0, 0, 1. They both have a third digit that's 0, which means that they're both round. But I don't need to know that they're both round. I just need to know they have a digit in common, that's 0.
Yeah.
So for Quarto, you've got 16 pieces. So you can refer to them as 0 up to 15, if you like. Those pieces, because those are those numbers in binary. And actually I have a set of at work I took a set of Quarto home, and I stuck labels on the bottom and wrote the numbers 0 to 15 on them in that order. And then if you arrange them in number order, you get a really nice pattern, because the way it goes, you've sort of got all the colours in stripes across. If you do it on a 4x4 grid,
I guess if colour's your first attribute, then every other binary number has a 0 or 1 in that position, so it'll alternate colours.
Yeah.
Yeah. Oh, that's sometimes.
And it alternates the other properties in different ways across your grid.
Yeah.
Which is quite cool.
We should make the photo for this episode be a picture of the pieces set up in that order.
Yep. Okay. Easily done. Good. Right. So then there are 2 things that we varied. Right. We varied the number of attributes each can take, and we varied the size of the board. There are a couple of other things we can vary if we want to go nuts. One is that we can vary how many values each attribute takes.
Yes, yeah, so instead of 2 to the n, you get powers of 3 or whatever. Yeah.
Yeah, so that's right. So we had, if we were allowing 3 heights and 3 colours and all that, then you'd have 3 to the power of whatever it was.
So could you then do a 3x3 board?
So then, yes, absolutely. So if you've got 3 to the m equals n squared, then m is 2 log to the base 3 of n, so you require n to be a power of 3.
Yeah.
So in this case, you could do a 3x3 board with 2 attributes, because 3 to the 2 is the same as 3 to the 2. Right?
Yeah, so then you're just looking for them to be like 3 of the same on one attribute in a row. I was sort of like, do you need them to be all different, but you need them to be all the same? I'm confusing it with set. That's what's happening here.
Right.
So set is this brilliant card game that mathematicians love, where everything's either red, green, or purple, and it's either stripy or filled in or not. And it's the same kind of idea, that you've got this sort of different properties that can take different values, and that's definitely I think is there 4 different properties, and there are 3 different values for each one. So that gives you a different, I guess, a version of this.
Yeah.
I wonder if you could play set with a board like Quarto and just place the cards on the table. I don't know.
There's definitely a link between them, isn't there? And there's also this thing that if you've got Quarto as 4 binary attributes, you can sort of make that 4 games of Quarto, or 4 games of 4x4 noughts and crosses. Because if you imagine that you're playing shape on the bottom layer and then colour on the next and whatever, it's like you're playing 4 games of 4x4 noughts and crosses at once, except that a move in one determines the move in all the others.
Yeah.
So you're really constrained over where you can play and what you can play. But that's one way of conceptualizing it, I think, is sorting that out. Anyway, so with your ternary attributes, with your 3 values for each attribute, the next board after a 3x3 board is 9x9 because it has to be a power of 3, and a 9x9 board uses 4 attributes. So even attributes, but a power of 3 this time. You can generalize that. You could have each attribute taking any of k values, so that there are k heights, k colors, etc. So then you would require that k to the m is equal to n squared, which would mean still m is still even because of the board size being the square, but now n has to be a power of k because you've got a log to the base k of n.
Yeah.
In there. That's fine.
Yeah.
That's fine. There is one number remaining in this.
Not yet
in this
varied.
form.
I think, is it the 2?
It is the
Is
2.
it the fact that you're playing on a crudely 2-dimensional board, constraining yourself to a flat game.
Terrible,
when
isn't
you
it?
could just be playing some kind of a higher dimensional Quarto.
So, if you wanted to play on an n by n by n cube,
Yeah.
what that would mean is instead of, because what you've currently got is little squares on a big square for a board, right? You've got 9 little squares on a square board. So in a cube, you'd have to have little cubes that each piece occupies.
Yeah.
One way to think of this is when you talk about higher dimensional noughts and crosses is instead of just thinking of the cube directly, you just think of 3 boards and they happen to be on top of one another. So you can do it that way. So you can have, a Quarto board with another Quarto board on top with another Quarto board on top of that. And you have to keep track of the fact that these ones are above each other. Like if it's stacked 4 high, you can have lines that are within each of the 4 boards, but you can also have lines that go between them, either vertically or diagonally or in lots of different ways. So if you're doing that, you've then got your k to the m equals n cubed for a 3-dimensional one. So now you need m to be a multiple of 3 and n to be log to the base k. So for example, if you had 6 binary attributes, you would require a 4x4x4 cube, which would give you 64 spaces for your 6 binary attributes.
Yeah, so it's on the order of the chessboard in terms of how big that would be to sort of think about and play. But
yeah. And so in general, you can make that dimension whatever you like. So
yeah, I was going to say, I think that's all the dimensions, isn't it? It doesn't really go
2
any
or 3.
further
That's
than
it.
that.
Yeah.
Yeah.
So in general, a d-dimensional board, you require m to be a multiple of d, and you require n to be a power of k.
Yeah, and you can't actually physically play the game, and you just have to imagine, or you can have.
You can play the game. I don't know what's wrong with you. You can play the game now. So my 2 examples in my slides here. I have 4 binary attributes on a 2x2x2x2 4 cube.
Yeah.
Would use 16 pieces. Because I've got 2 to the 4 pieces, I've got 2 to the 4 squares.
So you just get your regular Quarto set.
The advantage of that is you can use the regular Quarto set, that's right.
Punch a hole in the universe to put the game board in.
Well, I've also written here 15 ternary attributes on a 27x27x27x27x27 5 cube. Would use just over 14 million pieces.
Good.
For your 14 million squares.
Yeah.
But basically, so the 4 cube, what you do is, in the same way as I said, if you're playing in 3 dimensions, you just draw that many boards above one another. So if you're playing in, with 4 layers in, 4x4x4, then you just draw 4 boards on top of each other. Well, in this, if you're doing a 2x2x2x2 4 cube, what you need is a 2x2 square with a 2x2 square above it, and that's your cube.
Yeah.
And then you need another of those cubes just push it to the side in the fourth dimension.
Yeah.
But practically, you can just draw that next to it on a piece of paper. You don't have to worry about the fact that it's going into an extra dimension.
But you do have to remember that the bits in the same position on both boards are next to each other. I'm doing finger quotes around next to, although I shouldn't, because it is actually in the fourth dimension next to it, even though on your page they're on separate grids. It's part of the same line, I guess.
So what you've got is an enormous headache, but you said you can't play it. I'm saying you can play it.
I mean,
you need some rules about what's on top of one another. Yeah.
I feel like mostly when you try and do these things, you basically just immediately forget and accidentally win or accidentally lose without realising it. But
it's really hard to
as we've established, it's possible to do that anyway, just playing the regular game. So it's it's not that much more. It's the same number of pieces as the regular game, I guess.
Well, the regular game, if you get good at it, then you can invent an extra rule. You can add an extra rule that's in the book where, as well as 4 in a line, you can also do that each quarter of the board contains 4 and they can match in an attribute. And that, I think, is just adding another layer of cognitive difficulty. Yeah. I feel like if you get the hang of that, then why not do it in 4 dimensions?
Yeah. I also have a strong sense, because you mentioned that we sort of had this in mind as a topic for an episode since the very beginning. I'm sure that one of the very earliest ones we did was Noughts and Crosses. And we may have been through all of this in that episode as well. So if anyone's prepared to go back and listen, you may have just heard all of the same thoughts about how to play Noughts and Crosses in higher dimensions.
Yeah, that's possible.
But yeah, I think this is it is very like Noughts and Crosses in that it's just a very simple game where you take turns and you map the whole thing out. But I sort of like it because it's sort of nice to have a tactile thing to pick up and put down on a board, which you don't necessarily get with Noughts and Crosses, unless you've got like an actual Noughts and Crosses set that has pieces. But anyway, and it's also because it's a company that makes this as a version that you can buy. The same company has this whole range of really, really nice sort of logical, what we think of as mathematical board games. I think on their website they're listed under modern classics of abstract strategy, which is a nice way to summarise it. But they're all these sort of, games that just have pieces in 2 different colours, and they use like light and dark coloured wood, and it's all very classy. And they're all just very simple sets of instructions that you can put these games together, and they're all the kind of thing where you could, if you had some bits of card or a pen and paper, could reconstruct the game yourself without having to buy a copy of it. So they're really nice from that point of view, but they're also quite nice objects.
Yeah, they're
really
lovely. Good. They're lovely games, but also once you've got a notation, you can do what you want, right? So you can totally
just stand and shout binary numbers at each other.
So I had I had a student one year who we played. I think we might have played 8x8 Quarto, and we did it in correspondence mode during the Christmas break. So on Twitter we would send each other the coordinate and the piece that you wanted to put in that coordinate.
Excellent. Yeah, that's all you need.
Don't know how much strategy was going on because it was hard enough to keep track of what pieces were there. It's quite hard work in terms of cognitive load. But yeah. Anyway, so my advice is, if you've got k attributes and an n by n board, if you set n equal to k to the power of p for some positive integer p, then every positive integer p generates you a board, and you can use m equals dp for your dimension times the p to get you the number of attributes you need to fill that board. And so that means for every positive integer p, you can generate yourself a Quarto game for whatever dimensions and number of attributes you fancy. So, have fun.
Yeah. Oh, that sounds pretty conclusive. So, both Peter and I are on Twitter. I am at Steckles.
I'm at Peter Rowlett. The podcast itself is at Maths Objects.
And both Peter and I write for the blog at aperiodical.com, which is also where you can find more episodes of the podcast.
And if you have any thoughts or suggestions or ideas for objects we could talk about, or want to challenge us to a correspondence game of 27 by 27 by 27 5 cube Quarto, then you can email us at objects@aperiodical.com. And I'd like to thank Vincent Zazar for prompting us to do Quarto with a suggestion. Thank you.
The music is Funk Game Loop by Kevin MacLeod, licensed under Creative Commons.